Good morning, everyone. Hey, Isaiah. How's it going, Tyler? Hey, Amy, I got your email. I just have been too busy to reply. I apologize. You're going to be taken care of, though.
All right. I was going to say, it looks like you just changed the date on one of the tests I already took.
Uh-huh. Yeah, that's a possibility, but I prefer not to. I want you to have the experience of that test, just because that helps you for the final. So, the basics is of taking each of the tests. You're taking some 80 to 90% of the points of the final come from that original test. So that's why I don't want you to miss that opportunity. But I'll fix it up for you. It's just been a hectic week or two here. Actually, a week or 8.
Excuse me, sir?
I don't like my new job. I mean, I like it, but I don't like it. Yes, sir.
I couldn't help but notice
Matthew, do you have a
that
question?
we have 2 of the lecture classes today. Is that a glitch?
One of them is for a different one. It's
Yeah,
for
that was a
11
glitch in
a.m.
the recordings of Zoom. It's just, yeah, we'll have our lab at 1:30 like it's supposed to be, but no, you're not going to have 2 classes, not 2 lectures.
Okay.
And in fact, lab will be kind of short today. I've got another observational lab for you. I'll get you set up for that, and then you guys can go. So you'll probably be done with lab pretty early. I got to give you the time to go out and do the observations. So I usually take 20, 30 minutes to get you introduced to it and then let you go. Of course, you can stick around and ask questions if you have any, but mainly the main thing is getting you ready to actually go out and observe the night sky, because I want you to check out the winter circle before it disappears.
I just had a question about our lab for this week. Where do I submit? Because I saw in the rubric or whatever for it that we can submit it for astro points as well. Is there a specific section for each of those that we turn those in?
Yes, if you're in my lecture, I think I put the astro points link in last week's module for this course.
Okay, all right, cool.
Let me double check while we're here though, just to see.
All right,
see
thank
it
you.
already, or did you not?
I'm gonna go look at it right now.
No problem.
Good news, Professor Younger.
Okay, thank you.
Just three more moon observations left.
Awesome. I told you could do it, man. And you got plenty of time left. Remember, you can do more. It doesn't hurt. So nothing like that's going to be a problem. But yeah, so last week was week 9. And week 9, I have a chapter 9 with, no, that's the smart work thing. Oh, there it is. No, that's not it either. Warming. I'll put it right here. Where is it? Fiddle-dee-dee. Refresh my memory. What was it on? It was on the global warming stuff, right?
Yeah, the global exploration.
Yeah,
yes.
pretty sure it was.
Yeah, it was that wasn't it the using the web thing and then also the explorations? Yeah, I could have sworn I made it here, but I do not see it. I don't even see it in my AstroPoint section. I will make a link to that right after class. I might even do it during class, depending. Right? But I'll make it right here on week 9. Yeah, it's for lab, but what I told students is if you're in my lecture, you can get astro points for it there as well. So if you're in my lecture in my lab, you get astro points in my lecture, and then you get a lab grade in my lab. For those of you who are just in my lab, you get lab points. And for those of you that are in my lab at someone else's lecture, you may or may not get your instructor to take that as an assignment for astro points. So yeah, I will put it in week 9 astro points. Actually, I'll put it in week 9, 316 to 1155 on 322. So that'll be where that is. I see this. There's the PowerPoint. Yeah, it's weird. I could have sworn I put it on there, but I guess I didn't. Anyways, I've got some other stuff I put on week 9. You'll notice there's a photograph of the smart work due dates. So you might want to download that and stay ahead of it. And chapter 9 smart work, of course, is on there. I've also made astro points for chapter 8. You can see those in week 9 astro points. There's probably week 9 chapter 9 astro point documents, for reflection questions. I'll probably put those in week 9 as well. I haven't written them yet, but I will write them in the near future. So check the astro points every now and again just to look for any extra stuff that you haven't done. You'll see it in your grade book as well. So I did put up the lecture our PowerPoints for chapter 10, which is what we're covering today. So let me go ahead and get back to you guys, and we'll talk about that. Does anybody have any other questions before we get jamming on this chapter 10 stuff? All right, I guess we'll go ahead and go then. So I'm going to share my screen. I had a freak out this morning. I actually had prepped for class last night and today, like I normally do. But then I opened up the PowerPoint this morning and it said lecture slides, chapter 10. And then down here, it said the inner planets and the Earth's moon. I was like, oh, crap, did I read the wrong chapter? Well, come to find out, this PowerPoint, which was made by the publisher, just had the wrong slide as the first slide. It said the right chapter, it just didn't have the right title. So I changed the title this morning and posted that on Canvas, so y'all can check that out. This chapter is, like it says, it's on the worlds of gas and ice. And that's because we normally call the Jovian planets Jovian, or we'll call them the gas giants, when in actuality, it's really only Jupiter and Saturn that are gas giants. They're not as majorly, they're majorly gases, mostly hydrogen and helium, not unlike the sun. But Uranus and Neptune are actually more ices. In other words, they don't have that much hydrogen and helium. And the stuff that they do have is some of the ices. So what I thought I'd do is I'll start off like I normally like to do in my lecture. I usually don't do this in online courses, but I really should. So I'm going to go ahead and do it today. And that's just read off the learning goals for chapter 10. And the learning goals for chapter 10 are learning goal 1, differentiate the giant planets from one another and from the terrestrial planets. So this is a typical compare and contrast scenario, densities, orbital periods, orbital distances, rotation period, which is the length of a day, of course. Describe the atmosphere of each giant planet. And this is a really complicated issue with the gas giants and the ice giants, because specifically there's no there's no abrupt line between what's atmosphere and what's sort of solid material. So that's a little more complicated. Learning goal 3 is explain the extreme conditions deep inside the giant planets. Learning goal 4 is describe the magnetosphere of each giant planet. And then learning goal 5 is compare the planets of our solar system with those in exoplanetary systems. So in comparing to all the other exosystems we've seen, initially when we first started finding exoplanets, our ability to find them was really just based on whether the planet was big enough to perturb the orbit of the sun. And if it was, and we'd see it, well, lo and behold, guess what we found? A lot of big planets. And in fact, in order for them to actually perturb the sun very much, they need to be really close. So we had this really awkward period where we had this idea of how the gas giants were formed, and they all formed in nebular clouds way away from the star, because that's the only place these gases and ices could actually form in a liquid state. So when we found a bunch of Jupiter-sized planets that were way closer than Jupiter, then we were kind of at a loss, because that was like completely the opposite of our model. So it turns out now that that's not really the norm, that those are a little more rare than than that first experiments would have suggested. But that's, that should be expected. If you throw a net over fishing and you've got 8-inch holes in the net, and then you catch all these fish, you might reach the conclusion, oh, wow, all fish are bigger than 8 inches. Well, that wouldn't be a wise decision with it, because you just made a net that was only capable of catching fish bigger than 8 inches. So that's really what's going on here. So let's go ahead and get cracking on this. What causes the atmosphere features on Jupiter? And more specifically, what causes all these atmosphere features? It turns out, you know, Saturn might actually have a much more wild looking atmosphere, but we can't tell it because it's got this deeper atmosphere that's pretty much clear, that goes quite deep before you actually get to this sort of stuff. Whereas this sort of stuff on the surface of Jupiter, I say on the surface, on the upper atmosphere of Jupiter is right there in front of us, so we can see it really well. The other stuff looks way more subdued on Saturn, but that's not necessarily because Saturn's way more subdued. In fact, in many ways, we think it actually might be just as contrived and crazy. Of course, we know about the giant red spot, the Great Red Spot. It was discovered basically within 100 years after Galileo used his telescope. So we've known about it for 300 years, and at that time it was about 3 or 4 Earth diameters across. Now it's a little bit bigger than 1 Earth diameter. We've managed to see it, even though it's stayed or perpetuated itself. It's done a lot of changing here and there. We've had smaller cells come into it, circle around it, and get thrown out. We've had other cells come into it and get eaten, more or less. So all sorts of cool stuff. It definitely changes, but it's kind of interesting that it still persists. That was the word I was going for instead of perpetuates. What are the giant planets? Well, how do giant planets differ from the terrestrial planets? That's, you know, typical comparative planetology. What are the atmospheres composed of? Where do the extreme conditions deep inside the giant planets come from? What are the magnetospheres of each giant planet, and how do they compare to each other and to the terrestrial planets? And are there planets around other stars similar to the giant planets? So those are all big questions. I'm going to allow you a little bit more time to read yourself on that last learning goal. We'll go over it to some extent, but I just want to let you know, I want you to spend a little deep dive in that. You might even want to read the origin section at the end of this chapter, where you can learn about planets sort of migrating, which we've mentioned a little bit before, but it goes in a little bit more detail there. So Jupiter, Saturn, Uranus, and Neptune are giant planets. They're often called the Jovian planets because we actually use the Greek names, we use the Roman names for what was originally the Greek gods. So we use Jupiter instead of Jove, and we use Saturn and so on and so forth. So that doesn't mean that Jupiter and Jove aren't the same thing. It just means that we're using that more modern name. So sometimes if we want to distinguish it but still notate it, we'll just say they're the Jovian planets as opposed to the complicated Jupiterian planets, right? You could also call them like the 2 gas giants and the 2 ice giants. They are quite big. For instance, the diameter of Jupiter is about 11.2 times the diameter of Earth. I think I mentioned earlier, I remembered it being like 16 or something, but that was an error. I think that might have been the distance across the disk, or the rings of Saturn, but I could be wrong even in that case. But it's 11.2 Earth diameters is the diameter of Jupiter, whereas Saturn's like 8, and Uranus and Neptune are both about 4. So they're very, very big. In fact, Jupiter is also quite massive. It's 318 Earth masses, so that's pretty big. And another comparison is Jupiter is about 1/11th the diameter of the sun. So it's a really, really big thing. And in fact, if you want to go back and talk about the total mass in our solar system, remember we said somewhere along the lines of 99.99% of all the mass in the solar system is in our star, in our sun. And the other is all divvied up amongst the planets, the asteroids, the comets, the dust, the Kuiper Belt objects, which are most of the comets, the Oort cloud stuff. All that stuff is in that last 0.05% or whatever it is. Well, it turns out of that 0.05%, Jupiter's like 99.95% of it, or 99.5% of it. And in fact, Jupiter has twice as much mass as the other 3 Jovian planets combined. So it's really is the big dog in the neighborhood. And remember, if Jupiter had been somewhere about 75 to 80 times more massive, it would have actually been a star. If it would have been about 70 times, it would have been a brown dwarf. So that's really the dividing line. In other words, it couldn't have got too terribly much larger before it would have become a brown dwarf. And then, of course, beyond that would have been another star. Saturn is about 85% the height or the diameter of Jupiter. Jupiter has a density about 1.6 times that of the density of water. So the density of water is 1 gram per cubic centimeter. It's also a kilogram per liter. It's also a gram per milliliter, and it's also a 1,000 kilograms per cubic meter. They're all the density of water. Which is nice because it's always a multiple of 1 until you deal with salt water or something like that. And then it's like 1,025 or 1.025. But what we're saying here is this is slightly more dense than water. So if you found a big ocean, it would sink. But here's the neat thing. Saturn has actually got a density that's less than that of water. It's about 70% that of water. And if you found an ocean deep enough, when you brought it near the ocean, for starters, the ocean would be sucked up towards it because of the gravity. And then you slowly lay it in there. And in fact, it would float. Which is kind of interesting to think about, even though obviously we can't ever do that. Uranus and Neptune, they have higher densities as well. And if I remember correctly, Uranus is the most dense and Neptune is the second most, but I could be, I could have those backwards. You'll see it in your tables, and that's not the kind of things I normally ask you, except maybe once on a practice test or a homework or something like that. I don't normally make you memorize such things. Definitely not for the final, but occasionally for a test, you might see one question. One thing they do, as you can see here, and I said do. So this table actually lays out all that stuff we talked about. The distance from the sun is about 5.2 astronomical units for Jupiter. So it's literally 5 times farther away than Earth. So that's a lot farther away. Of course, in between there at about 1.52 is is Mars. And then of course the asteroid belt is in between Mars and it, but pretty much Jupiter is a really long gap away from Mars getting to Jupiter, on the order of 3.5 astronomical units. So 3.5 times the distance from the Earth to the sun between Mars and Jupiter is a pretty significant distance. Then if you look at Saturn, that's 9.6. That's almost twice as far as Jupiter is. And then if you look at Uranus, that's almost twice as far as Saturn is. And then if you look at Neptune, that's basically 1 1/3 times farther away. So these are really large distances that those planets are away. And in fact, Jupiter gets, Jupiter, Saturn, Uranus, and Neptune get very little light from the sun. If you were, for instance, on Jupiter, you could, make out that it's a disk, but it wouldn't be very bright. But on Saturn, it would just look like a pinpoint, as it would on Uranus. Very, very small amount of light. In the case of, I think your book mentioned in the case of Uranus, it would be a very brilliant star, about as bright as the full moon, but basically a pinpoint of light. Now, the orbital periods, because of Kepler's third law, these orbital semi-major axes make significant orbital periods. So we're looking at nearly 12 years for Jupiter, 30 for Saturn, 84 for Uranus, and 165 for Neptune. Obviously, those are very long periods of time. And if you think about the problem of Uranus, which you might recall from chapter 7, that it literally has been knocked over so that its orbital axis, or its rotation axis, is not perpendicular to the orbital plane, which is the ideal scenario where you have no seasons, of course. And the more you tilt it, the more extreme the seasons become, Earth being about 23.5 degrees tilt. But in the case of Uranus, it's literally tilted completely beyond 90. It's like 97 degrees. So it's completely upside down, more or less, but it's laying on its side in some sense. So like if Earth is here or the sun is here, we see Uranus orbiting rotating like this as it orbits. So that's kind of a weird scenario, but that's what it is. And because of that, it's got a pole that gets half of a year, a Uranus year of sunlight. And then that same pole, that same half of the planet gets half a year of nighttime, just like our Arctic circles do, except this is friggin' half the planet, right? And in fact, the equator is cold and the poles are hot. Of course, the poles also get the coldest of the cold, but they're also the hottest of the hot. So that's a pretty extreme scenario. Again, we think that was probably because of a collision or a number of collisions in the early solar system when it was sort of in a protoplanetary state. Here's the masses I talked about. The orbital velocities really don't matter, to be honest with you. That just allows you to make the math work. Basically, if you pretend they're circular orbits, then you can multiply, or you can take the distance around as 2 pi r and divide it by the period here and get these velocities. Even though they are somewhat elliptical, that's a rough approximation. But you know, you can't really do an experiment to detect the velocity of an object. That's what I mean by it's not that relevant. So it's just interesting to know that, yeah, obviously the closer you are and the higher your velocity is. And that also comes from Kepler's third law, by the way. It's just if you take Kepler's third law by setting Newton's law of gravity equal to centripetal acceleration times mass, then if you leave it in terms of period and radius, you get Kepler's third law that relates the square of the period to the cube of the semi-major axis. But if you leave it in terms of distance and velocity, you get this kind of relationship, and that would actually show you that the velocity does increase the closer you are to the planet. And that's a critical thing to understand when you go to try to think, well, which direction do the planets appear to move most of the time against the background stars? And which direction is it when they're in retrograde? That kind of stuff you need to understand the relative velocities for. Or for actually determining, as your book talks about later, how do we determine the radiuses of these planets? Basically, with the giant planets, one way you can do it is wait for starlight to be occluded or eclipsed, if you will, by a planet, and then you use the relative velocity of your planet and that planet, and that can tell you, based on how long it was blocked, tell you how big the planet is. So that's another useful thing. Here's the equatorial radii in kilometers, but like I said, the more relevant thing for us is about 11.2 times the radius of Earth, about 9.4 times the radius of Earth is Saturn, 4 and 3.8 is Uranus and Neptune. Because these planets are not solid, as you might expect them spinning, and you'll notice in a second that their revolution, their day, is actually quite a bit shorter than the Earth's because they spin so fast. And because of that, the poles actually get crushed, and the equators, whatever part is spinning perpendicular to the axis, that main part that's furthest out is going to be even further out. And in fact, we get an oblateness of 0.06 for the case of Jupiter, 0.09 for the case of Saturn, or excuse me, 0.065 and 0.098 for Saturn, 0.023 and 0.017 for Neptune. So that's markedly higher than, for instance, for the Earth is. Earth is quite a bit smaller oblateness. I think it's 0.3% or some god awfully small number like that. Rotation period, here it is. Jupiter, even though it's, you know, almost 12, well, it's 11 times the diameter of the Earth, it still rotates in less than half the time it takes the Earth to. The Earth takes about 23 hours, 56 minutes to make a complete 360. Remember, 23 hours, 56 minutes is a sidereal day, not the solar day. But this only takes 9.9 hours. Saturn takes about 10.7, Uranus takes about 17, and Neptune takes about 16. There's those weird tilts, and notice a 97.8 means it went further than 90, so that means it's actually going backwards too. So if it just went less than 90, then it would be tilted on its side, but it'd still be going the same general direction in terms of rotation, not revolution. The surface gravity for Jupiter is about 2.53. That turns out to be about like 26 or something like that, or actually it's a little bit less than 25 times the meters per second, whereas Earth is 9.8, which is roughly 10. So Jupiter has some serious surface gravity. Saturn has pretty comparable to Earth, only about 7% higher. Uranus is about 91% the gravity of Earth, and Neptune is about 14% higher. And then finally, you can see the escape velocities, which is relevant to what kind of atmospheres it can hold and stuff of that sort. The escape velocity is 59.5 kilometers per second for Jupiter. It's 35.5 for Saturn. It's 21.3 for Uranus and 23.5 for Neptune. Again, these are not numbers you have to memorize, but it's nice to know the relative sizes, for instance, the radii of the planets compared to the Earth. That's a figure that I expect people to know. I also expect people to know that, you know, maybe Jupiter is 318 times the mass of the Earth, and about 1/10 or 1/11 the diameter of the sun. Those are probably the only factors or facts I would really expect you to have in your brain at any time. They're called giants because of their mass, from 14.5 Earth masses up to 318 Earth masses. That's Jupiter. They have no solid surface really, but what they have is a ever increasing density of atmosphere that eventually becomes so dense that you can't penetrate it, which is in some sense like a surface, but it's, you know, it's still not really a surface. It's kind of a complicated issue. Okay. We just see the outermost cloud layers. We're sort of lucky in that the outermost cloud layers of Saturn are quite transparent, so we can see down into it, but they're not that transparent, so they give us this false sense that the underlying atmosphere is quite simple with regards to Saturn, and it's not. And we sort of get that same effect with Uranus and Neptune, not as much with Neptune as we do with Uranus, but all of that's somewhat of a ruse. They're very much active atmospheres. It's just there's a lot of stuff on the outside that sort of is making it look a little less crazy. Here's how you measure, for instance, and I think this diagram's backwards. I've been trying to figure this out since last night. It looks like it's backwards to me. Remember, the outer planet goes slower than the inner planet, so Earth should be blowing by here. But I would expect you to first see the star's light on this side of the planet, and then this side, but it's actually going the other way. So that kind of confuses me, but I don't know if that's worked out wrong or if I'm just not thinking it through clearly, but that's something you might want to look at and see what you think. It kind of bothers me because I know, like I said, the planets both go in this direction. This one being the inner planet is clearly going faster, but it seems to me like I would see the star way back here and then I wouldn't see it. And then, of course, if it was on this side, I would actually think, since this one moves slower, I would still see it when I went from here to here. That's why I really think maybe this ray was supposed to be here, and this planet was supposed to be here, and then this ray that's on this side was supposed to be here, and this planet was supposed to be up there where the top of the E is. I don't know, but either way, I think you get the point. Is basically the starlight from a distant star will be blocked by Jupiter or Uranus or Neptune or Saturn or Pluto, and the amount of time it takes to block it, if we take that and multiply it by the relative velocity of Earth with respect to that planet, then that would actually give us the, ignoring aberration effects like bending in the atmosphere and stuff like that, that would roughly give us the diameter of the planet. So that's stellar occultation. Occult, O-C-C-U-L-T, occult, is really the eclipsing, if you will. This is still the method for exoplanets, and that's, you know, kind of neat that we can do that. Planetary masses, of course, are found by using Kepler's third law. Remember, when Kepler introduced his third law, it would be of no use for finding the mass, say, of Jupiter or Saturn or even the Earth, given the moon. But when Newton comes along and derives Kepler's third law with Newton's law of gravity, then you have an expression for what that constant was. Remember, I said basically what Kepler found was that if you plotted the cube of the semi-major axis and the square of the period, then you got a straight line. And that just says that the cube of the semi-major axis is proportional to the square of the period. And then it's left to experimental evidence to tell you what that constant is. And because we happen to use units of years and astronomical units, in the case of Earth, 1 cubed is 1 and 1 squared is 1. So the constant has to be 1 when we're talking about orbiting the sun. So that constant just happened to be 1. But we don't really know anything deeper about that with Kepler's law because we just know it's proportional to. But if we go ahead and work out the details with Newton's law of gravity, then we find out that 4 pi g squared over m plus m, where the m is the mass of the sun plus the m is the mass of the planet, which is obviously way smaller than the sun in most cases. When you do that, that actually allows you to determine what the mass of the central body is. So if I find a Kepler's third law, which I will find for any object orbiting another object, in other words, if I actually plot a cubed and t squared for any other object orbiting anything, I will still find it's a straight line, but that slope will be different than 1. And that slope can be used, it can be set equal to this 4 pi g squared or whatever over m to determine the actual mass. So that's how we actually determine the masses of the planets. We get really excited if we find a planet, but we get even more excited if we find a planet with a moon, because then that allows us to determine the mass of the planet. Similarly, we get really excited when we find a new star, but we get even more excited if we find that star has a companion star or some planets orbiting it or something like that, because then we can determine the mass of that star as well. Does that make sense to everyone? I'm talking so fast, I need to force myself to stop every now and then because I get so, sometimes I get kind of excited about the material and I just keep blowing through, and I need you guys to make sure you ask me questions if it confuses you. Jupiter and Saturn were known to the ancients. In fact, if you look at the etymology of the names of our days of the week, basically they were named from the bodies that we see in the sky. I think you can obviously see sun in the sun in Sunday, and you can probably see moon in Monday, but that also gives you, of course, Tuesday, Wednesday, which comes from Woden, which is another form, if I recall my various languages that I've had the introduction to, I think is Jupiter. Saturn is Saturday, obviously. Thursday is Thursday, which I could also call Jupiter, but anyways, which I could also call Woden because I don't know that mythology that well. However, I do recommend you reading Neil Gaiman's mythology, is Nordic mythology. It's really cool, but that would get you a little bit of help in that. Either way, the big deal is that's where the 7 names of the days of the week come from, is the 7 bodies they could see. 2 of those were pretty obvious, the sun and moon, but the other 5 were the visible objects, which are Mercury, Venus, Mars, Jupiter, and Saturn. Okay, turns out you can actually see Uranus with the naked eye, but we didn't find it until quite some time later, and we found it with a telescope just more or less by an accident. But then when we were looking for something that was causing the problems of Uranus, we were actually able to discover Neptune. Now that was kind of cool because Leverrier and another gentleman whose name escapes me had calculated that the orbit of Uranus was not quite right. It was a little jacked up from Newton's laws of gravity and physics. And when you worked it out, you can see there was something making Jupiter's orbit behave badly. When they do that, they actually say, let's imagine over millions and millions of years that this planet has been orbiting around on the outside, and that actually caused the problem. So it would actually, in some sense, have a net effect of pulling out on the planet, and that would decrease the effect that the actual sun has on the planet. Well, if you're considering that over millions and millions of years, you might as well take a basically a ring of mass and put it completely around that other planet, and then divide that basically that distance by the total mass, and that would give you some idea of how big this planet would be. But when they did that, they were able to figure out that the planet Uranus was being perturbed by some other planet, and they could even narrow it down to roughly where it would be. And Leverrier and this other gentleman whose name escapes me, they basically suggested where it should look, and like literally within the same day, a person whose name also escapes me looked up in that site and found it immediately, found Neptune. Later on, they did the same thing with Neptune. They thought its orbit was screwed up, so they predicted another planet. That one was named Vulcan, not from, I don't think that was from Star Trek, because obviously it was way too early, but it was named Vulcan for a second, I think, and that ended up being just a miscalculation, but they did find Pluto, but Pluto was way too small to do that. So Uranus was discovered by Herschel. Again, like I said, that was an accident. Neptune was found because Uranus was straying from its predicted orbit. The gravity of Neptune was tugging on Uranus. There's the names: Leverrier and Adams. Adams was the guy who was mixing, and Gale, G-A-L-E, or Gali, I assume it's Gale. Gale was the guy that actually discovered it, but Leverrier and Adams predicted it. So it's pretty impressive work to be able to predict the existence of a planet, and not only that, tell you roughly where to look for it. We've done that before. We've been able to find bodies before by the way comets move, stuff like that, but it's really impressive, especially in the era of 1840s, because they're doing this with pencil and paper, no computers. It's a lot easier to do with computers. We see atmospheres, not surfaces of these bodies. The densities range from 0.7, which is that of Saturn, up to 1.6, which I said I thought was Uranus, but it could be Neptune, but I'm pretty sure it's Uranus. Earth's density is about 5.5 times the density of water. That's because it's rocky. So rocky planets tend to have densities from 3 to 6, stuff like that. That's what the Earth is right, smack in the middle of that. Jupiter's chemistry is mostly hydrogen and helium. In other words, it's about the composition of our sun. It's essentially 98% hydrogen and helium, and the rest is sort of trace elements, if you will. Saturn has more heavy elements, but is mostly like Jupiter. And Uranus and Neptune have more heavy materials, mostly methane, which is in a liquid and gas state, depending on what pressures. Now, one of the things I need you to understand is I've mentioned this before, that I saw some movie one time where they were trying to find the source of the Nile. And in the 1800s, the way you go about finding, and even the early 1900s, the way you go about finding the source of, say, a river, is you keep following the river until you find a big lake or something like that, and that would be the source of it. Or you find a mountain, say, with an ice cap that's melting and running down, something like that. But by necessity, since it has to be the source, it has to be the highest location along that river, right? Well, it turns out the higher you go in the atmosphere, the lower the pressure in the atmosphere goes. And pressure, you can sort of think of as like a blanket holding things down. So if you try to boil water, for instance, it'll boil once you get to 100 degrees Celsius or 212 degrees Fahrenheit. But if you imagine laying, say, a wet napkin on top of it, or a tarp on top of it, you can sort of see that napkin as being like some pressure that keeps the water from basically metamorphosizing from liquid to a gas, right? That's the same thing with air pressure. Air pressure actually, or any kind of pressure for that matter, actually makes it harder for that liquid state to transition into a gaseous state. And it goes to the next level. It makes it harder to go from a gaseous state, or let's say from a solid state to a liquid state. All those pressures do those weird things to the boiling point and melting points of substances. So you can actually have, for instance, water in a liquid state at 30,000 Kelvin if you really wanted to, but that would have to be a great deal of pressure holding it under. And that's sort of the weird thing about these planets, because they have huge amounts of pressure. I'm talking millions of times the pressure at the surface of our atmosphere, at the surface of our Earth, is what these things are experiencing down deep below the heavy atmospheres of Jupiter and Saturn. So because of that, you get some really weird chemistry. For instance, we get liquid hydrogen, or excuse me, liquid hydrogen and metallic hydrogen, which are both really weird things. Basically, liquid hydrogen being that it should be a gas, but it's under such pressure, it's in a liquid state. And it's actually molecular hydrogen is what they call it, but it is in a liquid state. And then the metallic hydrogen also is in a liquid state, but it's under such pressure and temperature extremes that the hydrogen couldn't hold on to its own electrons. So it's basically free ions running around in there. And because, they're free ions, that's essentially a conductor. So that's why they call it metallic hydrogen. I already mentioned the methane part. So all giants have rapid rotation and therefore different amounts of oblateness. This oblateness, they also have different obliquities. Jupiter is 3 degrees and Uranus is 98 degrees. That's where they're talking about the tilting of the axis. I read the two words as if it's all from the same sentence, and I guess my eyes are bad. But oblateness is how much the poles are squished and how much the equator is bulged out. In the case of the Earth, we actually call it an oblate spheroid, because it's not really a sphere. It's a sphere that's been crushed and has the center is a little poofy like mine. The same thing with these planets, but since these planets aren't solid, it's even more severe. So you can see again, these planets also have tilts of their axis of rotation. In the case of Jupiter, it's almost none, so it's 3%. So it has essentially no quote unquote seasons, whereas Uranus has, like I said, the most extreme of seasons. Specifically, it has half of a Uranus year, the northern hemisphere, say, whatever you tend to call that, that northern hemisphere would get extremely cold and be completely black that whole half a year. And then the whole half of the next half of the year, that half would get nothing but brightness and get pretty warm. So that's the extremes of the seasons that we're talking about. Jupiter has strong dark bands. They call them the belts, and then the light bands are called the zones. So basically, when you're looking at it, you'll see dark, light, dark, light, dark, light, and they've chosen arbitrarily to call the dark bands belts and to call the light bands zones. So if you're looking at here, this is a zone, and this is a belt, and this is a belt. Okay, and you can see that the giant red spot is right smack in the middle of a zone. Okay. You can also see the interface between the zones and the belts is actually where a lot of wobbling goes on. And in fact, a lot of these little vortices occur. This one's kind of cool. Check out the vortices around the pole here. So, and actually, I don't remember seeing that photo in the textbook. Does anybody remember what the heading said that was from? I remembered seeing this once, something like this once on the pole of Saturn, but I think that was just a hexagon, not the actual vortices like this. Does anybody recall from their textbook or see from their textbook?
Can I take a guess as to what it is?
Sure.
Is that eye thing right there, the great red spot, caused by
this is
difference in pressurized gas?
Yeah, that's definitely the cause. In fact, it's an anticyclone. So we call hurricanes cyclones, and we call high pressure zones an anticyclone. That's what this is. This is a high pressure zone, and we can tell that because it's rotating in a counterclockwise direction. Whereas if it rotated in a clockwise direction, we would call it a cyclone, and it would be like a hurricane. What I was referring to, let me click right here. I've got another window open where I can actually look at the text. So I'm going to pull that open real quick and find what that image is from. Anybody want to take a guess like he did about the cause of the giant red spot? Anybody want to take a guess of which planet that was we were looking at with the cool circles around the pole?
It's got to be Jupiter, right? Like,
I don't remember seeing that picture in the book. I see. Oh, there it is. Yes. So it's figure 10.6. Oh man, that was Juno, but it was it's in the infrared. That's why I didn't recognize it. So let me stop share and start share again. And now we'll go here. There you go. So Juno images of cyclones at the North Pole of Jupiter. So this is the North Pole of Jupiter, and you've got all these cool cyclones, which of course cyclones I said would be low pressure zones, and they're around the pole, which means this pole, since it's not coming in, must be a high pressure zone, which would mean basically air is lifting, or I shouldn't say air, atmosphere is lifting at the center here, and these are all sort of anticyclones, or excuse me, cyclones that are actually, I said that backwards. These are all sinking. These are all these are all cyclones that are actually lifting air, and they're not unlike hurricanes. In other words,
why aren't they moving and why aren't they dissipating either?
Oh, they do. You're not seeing the motion because it's just a photo, but yeah, if you look at it over time, these things will completely rotate with the rotation of Jupiter, and they sometimes disappear. They don't necessarily persist all the time, but they could in some cases, like in the case of the giant red spot, it did persist. This was a storm, for instance, that popped up on Saturn at one time, that because of Saturn's nature, it holds, just like Jupiter, it holds storms for long periods of times. So this one ended up wrapping all the way around Jupiter eventually.
Wait,
this part B here is the eye of the storm in Saturn's north polar region. Yeah.
How long has that been
ahead,
around? That storm right there?
This one only lasted, I want to say, for on the order of a year or so. We saw it and then it disappeared.
Oh. Because when
I also got to see, when I was in grad school, I got to see go ahead.
When I first learned about like the red eye of Jupiter or the red eye of Saturn, like I always thought that it was always there. It persisted all the time.
Yeah, and so far it has in the case of Jupiter, not in the case of Saturn. This one was transient at best. 2010 It was, I think we discovered it roughly 2009, 2010, and it was gone, I think, within 2000, by 2011 for the case of Saturn. But like I said, Jupiter's is still there, but it has gotten smaller. So we know that it isn't permanent in the sense that it always has the same shape over time and the same size over time. So it does change in some sense, where it's just a matter of time before we find out whether it persists, more than say 800 years. It's a matter of about 350 more years.
Is there ever a possibility of having two of these eyes
sorry,
appear at the same time?
Yeah, they've had, and you can see right now, you can see some smaller eyes. They've had a ton of smaller eyes come in there, sometimes interact with it. We've never seen two like on distant parts of the planet that are comparable in size, but we see plenty of them. As you can see, here's 1, 2, 3, 4, 5, 6, 7, 8 of them right here, and those are essentially, they're actually the opposite. They're actually cyclones, whereas this is an anticyclone. So we see lots of them at any one time. But usually they're not as long lasting as the giant red spot on Jupiter, and they're certainly not as big, which again, Jupiter's about 11.2 times the diameter of the Earth, and this storm is a little bit bigger than the diameter of the Earth. So it's, on the order of 9% of the diameter of the whole planet is this ginormous storm. But at one time it used to actually be 3 to 5 Earth diameters, in which case it would have been more like 18%. Any questions on that?
Two more, and they're all rolled up into one. How big can these things get, and could they get to the point where it could take up like half the planet?
The second question is no. The first question is the reason why. Basically, they can only get about as big as this one is because this is the biggest band. Okay, so what we do know is they generally occur between belts and bands. And it turns out that Jupiter, even Uranus, is majorly affected by the Coriolis force. In other words, the Coriolis force has a much bigger force on the atmospheres of the gas giants than the sunlight does, partly because the sunlight's so far away. We're the other way around. Our planet doesn't rotate that fast, so the Coriolis force is not that big of an effect, and we're closer to the sun, so the sun's the bigger effect. You can have heat, for instance, hitting one spot of the atmosphere. Of course, obviously the Earth is rolling under it. That heat can actually cause an increase in pressure. That actually causes things to blow outward away from it. But then the Coriolis effect causes it to curve to the right in the northern hemisphere and to the left in the southern hemisphere. It turns out on these planets, the Coriolis force is the biggest. So you have these zones of basically pressure regions are more like jet streams, if you will, in zones and belts going across. So we would never expect one just from a hydrodynamic standpoint. You probably wouldn't expect one to be any wider than a belt or a zone. And the biggest belt or zone is this one. So it shouldn't be any bigger than that. And we certainly wouldn't expect it to go across two of them just because the Coriolis force is such a large effect on these gas giants.
One more question.
You can see here, these are yeah, go for
it. The planet that's underneath all the gas, how can we estimate how big it is?
Yes, we have models. Originally, it was thought that all these planets had something comparable to Earth, but probably even bigger than Earth at its core. We're not as certain about that anymore. We do know there's, iron and nickel type compounds and minerals and stuff that would be dissolved in the cores of them, but we're not sure that they're really, like a hard seed in the middle. I think the current estimate is that probably Uranus and Neptune might have them, but Saturn and Jupiter probably don't. But we're really not completely sure on it. Okay, so that's definitely like an ongoing speculation. We don't have the ability to drill in. All we have right now are models of how fluids behave, and those models aren't even good enough to tell us how how this is happening. I mean, we have some idea how you can make a vortex, period. That's not a big deal. But why would a vortex be on something that rotates that fast on a very specific spot on that thing, right? We can't do that. So we don't know. We have an idea, and when you work out the models, and then that can give you roughly percentages of the compounds, elements, and stuff that are there. So we're not really sure, but we'll talk about it in a second. You'll see the actual diagrams of the inner parts as best we can tell.
So I can assume that since we don't even have
storm on.
I can assume that since we don't even have the size, we can't have the mass either.
Yeah, so we do have the mass, and we have an estimate of the mass that's not hydrogen and helium, and cooking all that up with all the models, we have a rough estimate of what we think would be the amount of the amount of iron and the amount of nickel that's in there. But we do think it's all less than less than like 0.5% or something. So it's a small amount, but 0.5% of the mass of Jupiter. Jupiter's 318 times the mass of Earth. So 0.5%, 1% would be 3.18. Half of that percent would be 1.5. So it literally would have almost 2 times as much carbon or iron and nickel as the Earth could, and just be a regular core inside of there. We do see these little wiggly lines, which are basically indicative of the bands of a jet stream falling towards low pressure zones and running away from high pressure zones. That's what this diagram is showing here. So these objects do have violent storms. We've seen them on all 4 now. And we've seen them last for long periods of time compared to storms on Earth. But again, in the case of Jupiter, that one's been there for at least 300 years. In the other cases, they're on the order of years, but not hundreds of years yet. Here's one, for instance, on Uranus. And these are infrared observations, show details of the structure of Uranus. There is a weak banding on both Uranus and Neptune. The banding, again, is like the zones and the bands. That again tells you the Coriolis force is the major effect. There are small, scattered, bright or dark clouds, and these planets have transient large storms, meaning they come and go. There's a great dark spot on Neptune. That's what you're seeing there. That appeared some time ago. I would say on the order, I think, if I remember correctly, on the order of decades. So it's been there a while. You see that. We also see, for instance, on Saturn, there's a hexagon on the poles, and that's just there, right? I think we've never seen that disappear, but you can sort of make sense of that with the ideas of laminar flow and how fluids flow in general. I don't think they completely explained it, but it makes some sense of it. When you actually look at under the cloud tops, in other words, as you go through the atmosphere, you can see Jupiter, basically, we go from the gaseous hydrogen, helium, methane, ammonia, and water down here. It actually has quite a bit of hydrogen helium mixture. And because of that, the helium can break off and become sort of other neat things. We have water ice down here. So the big thing when you're looking at clouds on these gas giants is the colors that you see are indicative of the elements that are present. And the elements that are present that you see are indicative of the temperature at which they're down. So if you go down further in the atmosphere, you reach different temperatures, as you can see. For instance, at an altitude of 100 kilometers, you basically have a temperature near 0 Kelvin. But as you get to say 0 or say 100 Kelvin, you might have some other things occur. But notice what's happening as the temperature gets lower and lower, other things condense out. Remember condensation? Like when you take a hot drink outside, immediately water condenses on the outside of the bottle. That's because the bottle is at a colder temperature than the air can sustain water. So the air touches it, and that water condenses out into little droplets on the outside of the bottle, basically because you've exceeded the melting, or excuse me, the condensation point for the air. The same thing happens here. Once you get to a low enough temperature, then you end up going from the gas being in a gaseous state to the gas condensing out to a liquid state and making a cloud. So you'll see, you know, purplish clouds are ammonia ice, and you'll see orangish clouds are ammonium hydrosulfide, and blue clouds are water ice, and so on and so forth. So it's kind of neat thinking about it that way, that when you look at these clouds, not only are their colors telling you the elements, they're also telling you the temperature. Because once you identify the element, you know what temperature it condenses out at, so you can figure that out. So the temperature and pressure increase basically going downward in general, okay? So the deeper you go, the more pressure it gets and the hotter it gets. We do have areas in our atmosphere in the Earth, which is much less dense, where it sort of goes back and forth. And in fact, they name the layers based on where the temperature starts changing from going down as you go up in altitude to going up. That's actually what we use to name the various parts of the atmosphere. Generally speaking, when you're outside of quote unquote the atmosphere, or excuse me, when you're inside of quote unquote the atmosphere, these suckers just warm up and increase in pressure. So, and as I told you before, pressure makes the boiling points and condensation points different than they would be on Earth. So yes, you'd expect water to condense out into a liquid state from a gaseous state at 100 degrees Celsius. But if you put it out under high pressure, it might actually occur at an entirely different one. So we got to take that stuff into consideration as well. So the clouds of Jupiter consist of ammonia, ammonium hydrosulfide. Ammonia is NH3. That has a temperature around 133 Kelvin. Ammonium hydrosulfide has a condensation temperature around 193 Kelvin. And you can see the different colors. Like I said, the oranges are ammonium hydrosulfide, and the ammonia is the actual purple. The highest clouds on Uranus and Neptune are methane ice. They are bluish because of the scattering of methane. So if you'll notice, Uranus looks sort of blue and Neptune looks sort of green. And that really is, again, the composition of it. It's mostly methane that gives it that bluish green hue. But other things and other elements, trace elements, can make it look more green or more blue. Basically, again, it's scattering, the same reason why our sky is blue. The particles interact with light that's about the same diameter as the wavelength of the light. So the blue light, of course, is the shorter wavelength, blue 2U, and therefore it interacts with the biggest parts of light because it's down at the smallest possible wavelength, which is, you know, visible light still bigger than wavelengths of light, but the blue end is the shortest wavelength, so it can actually interact with it. So when you get blue light hitting atoms in the atmosphere, molecules in the atmosphere, they can tend to get scattered to large angles, whereas the red sort of just barely passes by because it's, you know, so much bigger, it just almost ignores it. And because of that, every single molecule over top of you has a tendency to shoot blue in every direction, and some of those directions are your direction. So over here, a lot of the blue comes from all these particles all the way around. So you're getting blue from everywhere. Now, if you look directly towards the sun, well, that's where you're seeing the light that goes the straightest, because the light's coming from the sun, it's headed straight towards you, and the light that deflects the least is the red light, and that's why the sun looks, you know, mostly red, whereas the rest of the sky looks blue. Same thing here, we got the scattering going on from methane, and that basically, again, makes the blue scatter more, and we see blue all around it. Like I said, Jupiter and Saturn also are colored by impurities, so it's not like, you know, there's some jerk from Dr. Seuss polluting the planet. We just mean impurities in the sense that if you're looking at pure methane, anything that's not methane is an impurity. So that's what we mean by that. Windstorms. So this is actual wind profile for the various planets. You can see basically at 0 latitude, they tend to have the highest winds, and they're obviously going from east to west. Okay. I'm trying to remember if that's what I concluded about that direction. Either way, when they're going this way, they're going the opposite way. And whenever you have that, that makes one of those zones or bands. When you have wind going one way next to wind going the opposite direction, one of those will be a band and one of those would be a zone in the case of Jupiter. Otherwise, they're just regions or belts, if you will, of sort of jet streamish type characteristics. So the internal heat from the sun have a big effect on the global circulation pattern, as does the Coriolis force. The rapid planetary rotation results in the strong Coriolis force. Coriolis force is directly related to how fast the planet rotates, and it's also related to the radius. So that's why we have a huge Coriolis effect on these planets. The most extreme equatorial winds are in Saturn and Neptune's atmospheres. They actually have maximum speeds of 2,000 kilometers per hour. Can you imagine a hurricane that has, let's say, 1,700 mile per hour winds? You know, worst case scenario I think we've ever seen on the Earth in human times in recorded history is something like 220 gusts. And I think they had sustained winds of 200. That's remarkable. So imagine 1,700 mile per hour winds. That would be a beast. And Uranus and Neptune, Uranus and Neptune, they have alternating east winds, and they make bands of clouds as well. And the circulation pattern is different from planet to planet, and we don't really understand it that well. In fact, we also got some limitations because of those large orbital periods. I think one was 84 years and the other one was 160 years. And Uranus being tilted over, we only get to see the northern hemisphere for for Uranus, we only get to see that for like 40 years straight. You know how much has happened in 40 years? We've gotten a lot of technology that would allow us to see a lot of things about Uranus, but all of that's been in the last 20 to 30, 40 years. All of that stuff hasn't been able to see the other side of Uranus at all. And if you're talking about Neptune, is even worse because that's going to be 90 years of seeing. Of course, that one's not tilted over, so you don't have the pole problem, but you still have the problem of seeing it from different angles in the sky, causing somewhat problems. But Uranus is the major one just because it's completely tilted. We can't do much. Again, we don't understand a lot of circulation patterns. So this is what planetary astronomers, which is what Carl Sagan was, Carl Sagan was. That's what they do. They try to figure out what is similar about these planets and Earth and what is different and what makes the difference and what, is there new physical principles? Are there new physical laws maybe that Newton and other people hadn't discovered yet that we can make sense of, use to make sense of the planets, and in fact might even come back to make sense of our own planet. Here's the models of the interior, Matthew, that I was talking about. On Jupiter and Saturn, at depths of a few thousand kilometers, the gases are compressed so much they liquefy. This is that principle again. Even though the temperature is well high enough for these gases to be in a gaseous state, they're not in a gaseous state because they're under so much pressure. At high pressure and temperature, this liquid hydrogen can act like a metal. Again, it's basically been stripped of its electrons, and anything that has free charge carriers around in the material is a metal. That's a conductor. That's the definition of how conduction works. So that's what we're talking about here. Jupiter's core pressure is 45 million bars. So again, we're on the order of tens of millions of atmospheric pressures. Jupiter's core temperature is 35,000 Kelvin. That's even obviously hotter than the surface of the sun. The surface of the sun is about 5,800 Kelvin. So this is hotter than the surface of the sun. Of course, we're not getting anywhere near that 10 million Kelvin that's needed for fusion. And that's because, obviously the sun is a star, and Jupiter didn't become a star, and certainly Saturn and Uranus and Neptune didn't. The cores are a liquid mixture of water, rock, and metals. So you can see basically the way they break this down. The red is rock material. The blue is ice materials. That means not just water ice. That means ammonia ice and ammonium hydrosulfide ice, stuff like that. Metallic hydrogen is the gray, and then that sort of aqua greenish color is molecular hydrogen. That's H2 is what they're talking about there. But you can see with Jupiter, you're going to have the ices outside of the rock. And if you notice this compared to Earth, that's about the same size as Earth, if not slightly bigger. So we do expect it sort of has this rocky core and all four of them, but we're really not that sure. That's something that's ongoing. There's some planetary astronomers that believe there might not be a rocky core in there, and there's others that believe that rocky core or not, these planets were not created at this particular point in the solar system, that they were in fact migrated to where they are now from either farther out or nearer in. So those are some of the ongoing questions in planetary astronomy right now. as I said, there's no clear-cut boundary between the atmosphere and the underlying oceans. Remember, we're interacting with a gas that's slowly becoming a liquid. So that's why we're calling it the underlying ocean, because it really is a liquid, even though it's liquid, metallic hydrogen. That's a big deal. And liquid molecular hydrogen, that's, another big deal, but it's still a liquid. So it's very much like a sea, but a liquid. And it would be, obviously, you'd think of it being, since it's a gas, hydrogen that always appears in the gaseous state. Clearly, if it's in the liquid state, it must be butt ugly cold. But lo and behold, no, it's not butt ugly cold. We find in the core it's 35,000 Kelvin, and it's considerably higher up here. Or excuse me, not nearly as high up here, but still considerably higher than Earth temperatures. Let's put it that way. Uranus and Neptune are smaller and have less pressure than the gas giants. Whoa. They have more water and ices, ammonia and methane ice, for instance. Deep oceans containing dissolved gases and salts are present. Those salts, by the way, can also cause ionization. They can cause rain to cause lightning bolts. So, for instance, when these things condense out and actually become liquids, then the actual sort of rain falls. And when the rain falls, the rain can actually hit molecules and strip electrons from it. That makes the molecules and atoms ionize. That ionization will cause the material between, two charged objects to become basically a conductor. When it does, that's a lightning bolt going from one to the other. It turns out we see a lot of lightning on all four of these. So they all have lightning, and it's sort of a weird lightning in that it is going through an atmosphere, but the atmosphere is so very different. But that's basically how that works. The computer simulation suggests that the water on the ice giants is probably superionic, a state between liquid and gas. Superionic, remember, if you take a gas and then you subject it to such high temperatures that the atoms in the gas can't hold the individual electrons to it, then the atoms become positively charged, and the loose electrons, of course, are negatively charged. What you have then is a plasma. And that is another state of matter that we've named plasma, specifically because it doesn't behave like a gas, a liquid, or solid. You remember, a solid has its own volume and its own shape. A liquid has its own volume, but not its own shape. It takes the shape of its container. A gas has neither its own volume nor its own shape. Plasma doesn't have its own volume or its own shape, but it can also be manipulated not only by physical objects, but by a magnetic field. So now we've got this, which is a liquid ionic state, which, is sort of like liquid plasma, if you will. So it's definitely a weird thing, and it's stuff that we don't get to interact with as much as we do in everyday life. So just human understanding isn't that good, but the upper echelon planetary scientists and hydrologists and people that study hydrodynamics, they might know. I shouldn't say hydrologists, except in the sense that it's about hydrology or hydrodynamics. Hydrologists have a name specifically in the regular engineering world as the people that study groundwater. So I didn't want to, not to say either one's bad or good, just to say that they're definitely different when they're studying this kind of stuff. The magnetic fields are generated by the motion of the electrical conducting liquids. Again, just like we don't know exactly how the Earth created its magnetic field, we call it the dynamo effect. Well, we're using the same kind of idiocy here. We really don't know. I mean, we have an idea. We know that you can create magnetic fields and electromagnetic waves from charges accelerating. So if you have ions inside of something and it's rotating, it's automatically accelerating. So that can produce electromagnetic radiation, which might be seen as the cause of the magnetic field. But then we have these weird anomalies that we can't explain at all. Like Jupiter's awesome. It's got basically only a 3-degree axial tilt, but the magnetic field axis is misaligned both with angles. So I think it's off by like 9 degrees. And then it's not centered on the actual planet either. So the center of this bar magnet is not at the center of Jupiter. Saturn, on the other hand, is right on the money. It's tilted at, within a degree or so from the actual rotation axis of Saturn, and it's almost right on the money for the center being at the center. So it's got the most spherically pleasing or symmetrically pleasing magnetic field, even though Jupiter's is way, way bigger. In fact, your book calls Jupiter the largest permanent object in the solar system. It's, more than 10 times the size of the sun. Uranus has another one that's way off center and way off axis. In fact, it's, well over 45 degrees off axis. This one's close to 45 degrees off axis, and look how far off center it is. So we don't understand this. We don't understand why we should model the magnetic field as a bar magnet that's so far off center and so far tilted. That's ongoing research, maybe even Nobel Prize winning research if someone can figure that crap out. But it's got to be, and this is the rub, it's got to be something you can figure out theoretically and then confirm it. You've got to make experiments that someone could go and say, okay, well, this is that. So even if you do get that, you're probably not going to get the Nobel Prize because it's going to take another 10 years before they can test it, more than likely, because everything takes 10 years of development, bare minimum, to go to space. So for the ice giants, their orientation is an angle to the rotation axis and not oriented in the center. And the reason for this strange geometry is not well understood. Your book models not unlike a ball of algae on a rock in a stream. The algae, of course, falls down and it's got its own impetus to lean outward, but the oncoming current's got an impetus to push it away, so it reaches some equilibrium where the two meet is called the bow shock. And then this is the tail, if you will. And Jupiter's magnetosphere is, in fact, so long that it goes beyond and interacts with Saturn and its moons. So it's pretty impressive. They interact with the solar wind. They produce auroras, just like we have aurora australis and aurora borealis. They have those on Jupiter. In fact, Saturn's got some really cool ones, specifically because it has not only this thing going on, but it has the moon Io, just like Jupiter has the moon Enceladus, that sort of contributes to it. But Enceladus doesn't do nearly as much as Io does. So Saturn gets this torus around it from Io, and then it's got this flux tube that sends ions back and forth from Io through the aurora, if you will, of Saturn. So it's some really cool stuff to see. They produce radiation that we can pick up on the AM radio stations here at Earth. They also produce what's known as synchrotron radiation, and that synchrotron radiation is locked to the very bar magnet type models of the magnetic field. So that's our truest indicator of the periods of rotation of these gas giants. Here you are seeing some of the auroras up here. This is the flux tube we were talking about, and this is the torus caused by Io around Jupiter. As far as exoplanets, we found numerous ones: Kepler 20b, Kepler 20e, Kepler 20c, Kepler 20f, Kepler 20d. Basically, initially we found hot Jupiters. Later, we found what we called puffy Jupiters that have a larger radius but lower density than Jupiter. Super Jupiters have masses of 2 to 13 times Jupiter's mass. And then super Earths and mini Neptunes are 1.5 times the Earth of the mass, the Earth's
2
mass.
minutes left.
That's it, basically. I've finished. As I told you, I wouldn't do much with the exoplanets. That field is changing so quick. I don't spend much time in trying to cover it with you, because you can literally go to using the web and reading astronomy news sections of your textbook and find by going through the acts that they suggest you do, you'll find way more information on exoplanets, because literally we're finding right now, I think, on the order of hundreds of planets a year. So, forget about it. You can't write a textbook on that stuff. You can just say, oh, well, we're finding a lot of planets. So anybody have any questions? I'm going to put up a link for you to turn in last week's lab for astro points on this week's module within the lecture portion. I'm also going to post the lab for this week on the lab portion of Canvas. So that'll be up there before you have lab. We're going to meet at 1:30 for lab. It will be a short meeting, but it's me using some tools to show you how you're going to go about finding some different constellations in the skies, specifically 6 constellations: Canis Major, Orion, Taurus, Auriga, and then Gemini and Canis Minor.
I have a question.
So we're going to find those 6 constellations. I'm going to tell you how. This is something you can do very easily, even in downtown Virginia Beach or Norfolk. So yeah, go ahead, Matthew. Y'all are free to go, by the way. Just make sure you get your test done. I put the test up. It's due on Wednesday. I made for you guys. So that's on chapters 7 and 8. It's already up. The practice test has been up for a while. Y'all can go ahead and get that done by Wednesday at midnight. All the chances are due. Go ahead, Matthew.
Did you just say that we turned in last lab to the lecture, you said?
Yes, I told everybody if you have me for lecture, you can turn it in for astro points in lecture, and you can turn it in for a lab in lab. So it's sort of a double whammy.
That's actually pretty nice.
The using the web part was a significant amount of work.
Thank you, sir.
Kind of me, isn't it?
Thank you, sir. Have a very nice day.
You're welcome. Have a good one, Matthew.
Okay. Oh, actually, let me tell you something. Let me tell you something about about what happened. Okay, you remember how my birthday was like on the 18th, right? Okay, so
last Thursday or something. Yeah.
Yeah, I went to hibachi with my family. It was nice, right? Now,
Excellent.
Since it was my 21st birthday,
Yeah.
I had my first shot. That went over as well as you would expect it to be. I was giggling all the way home. I was just like, I don't know what's happening.
Did it burn your throat?
Huh? What?
Did it burn your throat?
Oh no, it was actually like I don't know what it was, but it was good tasting. I have no idea what it was. It was like a light blue, neon blue type thing. It was like
okay,
fruity,
so
tropical tasting.
That'd been a little easier on you. I was gonna say you got a future alcoholism problem in your future, but no, you'll be good, man. Just be careful with that stuff.
Yeah, I don't plan on drinking.
A lot of bad comes from what the chemistry of the liver does.
Oh yeah, obviously. Like I don't.
Anybody else have any questions for?
Okay. Well, see you, everyone. Have a wonderful day. See you, Mr. Younger. I'm gonna head out.
Have a good one.
You too.
I had a couple of comments based on what you were saying. So
go ahead, Amy.
The reason they named the planet Vulcan wasn't necessarily a Star Trek reference. That is the Roman name for Hephaestus. Because all of the gods.
I was wondering what I was thinking. The mythology might have been Norse, but yeah, it's Vulcan. Yeah, that's right. You're right.
Norse mythology is all of the days.
What else were you going to say about Hephaestus? Was the equivalent of Vulcan?
It was Hephaestus, yeah.
What was that about Saturday? I missed it.
Saturday is the only day of the week that isn't with Norse culture, and that's based off of Saturn.
Right, gotcha.
Like
the Norse culture is very big in the etymology where you trace out the names Thor and Wu and.
Yeah.
Are you a big fan of Norse mythology?
I'm a big fan of all mythology. I have American Gods. I have yet
all of
to
them are
read
cool.
I've been so busy. But
American Gods is great, but he went back after that and wrote a book on it's just called Norse mythology. Neil Gaiman did, and that's really great. There's also a really wonderful mythology textbook that I have that was something like it was some title like Zeus has questionable sex with weirdos or some crap like that. I mean, it's literally one of these type off the wall books. I'll find out the title and post it for you. It's one of the books that they were using for mythology at TCC, so you might know it already.
That's fantastic.
Or Zeus grants weird wishes. Yeah, it's really cool. And they go through, Indus types of mythologies, Arabic mythologies, Chinese mythologies. Sorry for calling something Chinese as opposed to the whole Eastern mythologies. But yeah, they go through all those different ones, and they tell them, kind of comically by, referencing stuff like people acting like pimps and stuff like that, as opposed to just using the stiff language of modern life. So yeah, I'll send you an email or post it or something about that textbook I have. I've got it in an ebook edition as well as a paperback.
That would be fantastic. Thank you.
You're welcome. Anybody else have any questions or anything? Thanks for your information, Amy. Have a good one. Jamie or Mason, you got any questions? All right, we'll call it a day then, folks. Y'all have a good one.